Hello and welcome back. In the previous video, we studied the kinetic energy that is associated with the random motion of molecules inside an ideal gas. In the next few videos, we'll be discussing the laws of thermodynamics, with a particular emphasis on the ways in which we can convert this random energy that is stored in a gas into a useful form of energy which we can use to do work. Now, when we discuss the laws of thermodynamics, we'll often talk about the internal energy of a gas, which we denote with this capital letter U. And basically what the internal energy of a gas is it's the energy that is associated with the atoms or molecules inside the gas. So for example, in the previous video, we found that the kinetic energy that is stored inside an ideal gas is equal to 3/2 nkt, where n is the number of molecules in the gas and T is the temperature of the gas. Now, while this formula is always true, it turns out that there are other types of energies which can contribute to the total internal energy of the gas. For example, if we consider something like a diatomic molecule, so this is two atoms that are connected together by a single bond. Not only is there energy associated with the translational motion of the molecule, so the whole molecule might be moving with some speed like this, there is also energy associated with rotations, so the molecule might be rotating about a central axis like this, or it can be rotating about a vertical axis like this. In addition to these two axes, there is a third axis which runs down the length of the molecule. However, there is very little kinetic energy that is associated with rotations about this axis. In addition to the energies that are associated with the rotations of the molecule, there are also energies associated with the bonds itself. So, for example, we could treat a molecule as being like two atoms that are connected together by a spring. So there is an energy that is associated, a potential energy, that is associated with this bond. In addition to this potential energy, remember that when you stretch a spring and you let go of the mass will oscillate back and forth. So similarly, when the bonds inside a molecule stretch, the atoms on the ends of this molecule will vibrate back and forth. And there's a kinetic energy that is associated with this motion. So it turns out that the total internal energy of a diatomic gas is equal to the kinetic energy that is associated with the translational motion of the molecule, and this is that type of energy we talked about in the previous video, plus the kinetic energy that is associated with the rotations of the molecule, plus the energy that is associated with the bonds of the molecule. And this is both the potential energy stored in the bond and the kinetic energy that is associated with the vibrations of the atoms. And it turns out that there is a very simple theorem which allows us to relate all of these types of energies together. And this theorem is called the equipartition theorem. And basically what the equipartition theorem states is it states that the total internal energy of a gas will be equally distributed among the different types of energy. So for example, with translational kinetic energy, it turns out that there are three types of translational kinetic energy, one associated with each direction. So we've got the X, Y, and Z directions. For the rotational kinetic energy, there are two types of rotational kinetic energy, one associated with this axis that is going into the screen, and one associated with this vertical axis here. Finally, there are two types of energy that we associate with the bond between the two atoms. There's the potential energy, and then this kinetic energy that is associated with the vibrations of the bonds. And what the equipartition theorem states is it says that the energy for each type is going to be equal to 1/2 nkt. So this is why for kinetic energy we have it's equal to 3/2 nkt, because there are three types of kinetic energy. Now, it turns out that for most diatomic gases, we don't have all three of these types of energies present. The reason is that because of quantum mechanics, there is a minimum kinetic energy associated with the rotations and a minimum energy associated with the bonds between the atoms. So if the gas is very, very cold and it doesn't have very much energy, it won't have enough energy to allow these types of rotations or the bond stretching. So for temperatures that are very low, so let's say typically around below 10 Kelvin, the only thing you have is the kinetic energy associated with the motion of the molecules. And in this case, the internal energy will just be equal to 3/2 nkt. Now at higher temperatures, like room temperature, you have energy associated with the motion of the molecules as well as energy associated with the rotations of the molecules. However, at room temperature, there's still not enough energy to actually stretch the bonds of the molecules very significantly. So at room temperature, the internal energy is going to be something like 5/2 nkt. It's 5 halves because we have 5 types of energy. We have 3 associated with the kinetic energy and 2 associated with the rotational kinetic energy. Finally, at higher temperatures, so at temperatures that are above, typically we're talking about above several tens of thousands. I'll just write above 10,000. But typically we're talking about 60 or 80,000 Kelvin before these other types of energies come in. I just closed that screen. But at very high temperatures like 60 or 80 Kelvin, the internal energy of the gas will be something like 7 halves nkt. Now, most of the time, when we're dealing with these types of problems where we'll be using the internal energy of the atom and we'll be relating this to the temperature, so when we want to know how the internal energy depends on the temperature of the gas, we'll assume that the gas is monatomic. So we're just talking about a single atom. So examples of monatomic gases are things like helium and neon, or really any ideal gas. And when you have a monatomic gas, so it's just a single atom, the only type of energy that we can associate it with this is the kinetic energy that is associated with the motion of that atom. So for monatomic ideal gases, it turns out it's very, very simple. The internal energy will just be equal to 3 halves nkt. So most of the time when we're relating the internal energy of a gas to a temperature, this is the situation we'll be looking at. We'll be looking at a single atom moving around, and in this case it's a very simple relationship. So getting back to the laws of thermodynamics, basically all the first law does is it simply restates conservation of energy in terms of thermodynamic quantities. So what the first law of thermodynamics states is it says the change in the internal energy of a gas is equal to the heat that is given to the gas plus the work that is done on the gas. And we have to be very careful when we use this formula that we use the correct signs for Q and W. So here I say that Q is equal to the heat that is transferred to the gas. So this means that, for example, if you have something like a combustion engine where there's gasoline burning, it's heating up the gas inside a piston, then you're giving heat to the gas. So Q will be positive. Or if you take something like a gas and you place it on a burner on a stove, then you'll be giving heat to the gas, so Q will be a positive quantity. Conversely, if the gas is losing heat to its surroundings, so heat is leaving the gas, then we say that Q is negative. Similarly, we have to be careful about the sign for work. Okay? So what does it mean to do work on a gas? So an example of this would be like if you have a bicycle pump and you push down on the plunger of the bicycle pump, then you're doing work on the gas. So in that case, the work that you do is positive work, and it will increase the energy of the gas. Conversely, if a gas expands, then work is being done by the gas. And in that case, we say that the work is going to be negative, because as the gas does work on its surroundings, it will lose energy. So how do we actually calculate the work that is done by a gas when the gas either expands or is compressed? Well, recall that work is equal to force that is parallel to displacement times the displacement. So for a gas, when the gas expands, the force that causes the gas to expand is caused by the pressure of the gas. So for example, here I show a gas, and on the top we have a movable piston. And the force that causes the piston to move upwards is caused by the pressure of the gas. So remember that pressure is related to force by this formula here. Force is equal to pressure times the area of the surface. In this case, we're talking about the area of the piston. So work would be equal to pressure times the area of the piston times the distance that the piston has moved. And it turns out that we can rewrite this in an even nicer way. To understand how, let me go over here and just draw a little dotted line here that represents the initial position of the piston. So this A here is the area of this piston, and S is the distance that the piston moves upwards. So this product, A times S, is actually equal to the change in the volume of the gas, right? If I take the area of this base and I multiply it by the distance that it moves upwards, that's equal to the change in the volume of the gas. So I could rewrite this as being equal to pressure times the change in the volume of the gas. And lastly, we have to be a little bit careful about this. If the volume of the gas increases, then work is being done by the gas, and we call that negative work. So when the delta V is positive and the gas is expanding, then the work will be negative. So this is the formula we have for the work that is done by a gas when the gas expands. Now let's go ahead and look at an example. This first example says 3 moles of an ideal monatomic gas have an initial temperature of 345 Kelvin. We're told that 2,438 joules of heat are added to the gas and 962 joules of work are done on the gas. And the question asks us to determine the final temperature of the gas. So the first thing I want to point out is that we're told that the gas is an ideal monatomic gas. Remember, I told you that before at the very beginning of this video that most of the time we'll be dealing with monatomic gases. And what this means is it tells us that the internal energy of the gas is just equal to 3/2 nKT. Or we could write it as 3/2 number of moles times the ideal gas constant times T. And again, the reason that I can do this, there's one easy way to think about this, is that remember that when I go from a capital letter to a lowercase letter, I do this by dividing by Avogadro's number. So to go from this capital N to this lowercase n, I divide by Avogadro's number. Conversely, to go from a lowercase number, like this lowercase k, to a capital number, like this capital R, I multiply by Avogadro's number. So here I'm dividing by Avogadro's number, and then I multiply this by Avogadro's number. So in the end, those two things cancel out. So I have that the internal energy of the gas is just 3/2 nRT, where n is now the number of moles. So this is the relationship between the internal energy and the temperature. So using this, we can calculate the final temperature if we know how the internal energy changes. Now the other bits of information that we need to be careful about is that we're told that heat is added to the gas. So this means that Q is equal to plus 2,438 joules, because heat is being added to the gas. We're also told that work is being done on the gas. This means that the work is going to be positive 962 joules. Because work is being done on the gas, it means the work will be positive. So using the first law of thermodynamics, we have that the change in the internal energy is equal to the heat that is given to the gas plus the work that is done on the gas. And as I mentioned in the previous slide, the change in the internal energy is just going to be 3/2 nR delta T. So finally, just solving for this delta T, we'll see that delta T is going to be equal to, so I'll multiply the 2 over, so we have 2 times Q plus W, and then I'm going to divide by 3nR. And if I plug all these numbers into a calculator, so if I plug 2,438 joules in for the heat, and I plug 962 joules for the work, I'll see that this is going to be equal to 90.9 Kelvin. So that's the change in the temperature. Now remember, we were asked to find the final temperature. So change in temperature is final temperature minus initial temperature, and this is 90.9 Kelvin. So the final temperature is equal to the initial temperature plus 90.9 Kelvin, or 436 Kelvin. So this is the final temperature of the gas. In most situations, the pressure of the gas will change as the gas is either expanded or being compressed. So as a result, we can't simply say that the work that is being done is equal to the pressure times the change in the volume, because the pressure will be changing as the volume changes. Now we ran into a similar problem when we talked about calculating the work that is done by a force, right? So we say the work that is done by a force is equal to the force that is parallel to displacement times displacement. And we said that in a lot of situations this force might change as the object's position moves. And what we decided was that when we have something like this, we can calculate the work that is done by this force as being equal to the area that is underneath a force that is parallel to displacement versus displacement curve. So for example, if I have something that looks like this, the work that is done by this force is just equal to that area that's underneath this graph. Similarly, we now have that the work that is done by a gas is equal to pressure times change in volume. So this is just like force times displacement, where our force is now the pressure and displacement is replaced by the change in the volume. So if we plot the pressure versus volume for a gas, the area underneath this graph would tell us the work that is done by the gas. Now the thing about it is we have to be a little bit careful when we're dealing with gases, because remember, it depends on whether the gas is expanding or is being compressed. So for example, here I have arrows here that are indicating that the volume is increasing. Okay, and that's typically how we'll do this. We'll put little arrows on the line that show which direction it's moving. So here the volume is increasing. This means that the work that is being done is negative, right? The gas is expanding, so the gas is doing work. So the work that we would plug into the first law of thermodynamics is a negative value. So let's go ahead and look at a couple of examples. In this first example, we're given a pressure versus volume graph for something called a cyclic process, and we're asked to determine the amount of work that is done during one complete cycle. Now, I want to talk about cyclic processes just a little bit. Cyclic processes are an extremely important type of thermodynamic process because it's the type of process that appears in things like engines. And a cyclic process is a thermodynamic process that ends in the same state that it starts at. So for example, here we start at this point A, we go to B, C, D, E, and then we go back to this point A again. So we're going to end this process at the same place that we started it. One important thing to keep in mind about cyclic processes is because the ideal gas law says that PV is equal to nRT, and because in a cyclic process the initial pressure is equal to the final pressure and the initial volume is equal to the final volume, we have that the initial temperature is always going to be equal to the final temperature. And this means that the change in the internal energy is always going to be equal to 0 joules. So recall that the way that we calculate the work that is done when the pressure of a gas is changing as it expands is it is equal to the area that is underneath the pressure versus volume graph. So for example here, this work is going to be equal to this area right here. So if we look at the shape, we can see that it is a trapezoid. So the work that is done when I go from A to B is equal to the area of this trapezoid. And remember that the area of a trapezoid is given by the height, it's the base times the average height. So that is 1/2 times, so the height of this graph at point B, I'll call this the pressure at point B, plus the height of the graph at point A, which is PA. So it's the average of these two heights times the base. So the base, I start out at some initial volume V0, I go to a final volume 2V, so this length of this base right here is equal to V0. We multiply this by 1/2 times the sum of these two pressures. So the pressure at point B up here, this is 3 P0, so we have 3 P0 here. The pressure at point A is 2 P0, so we have plus 2 P0. So if we plug all this in, we see that this is equal to 5/2 P0 V0. And the last thing we need to do is we need to be a little bit careful about the sign. So when I go from point A to B, the volume of the gas is increasing. So the work that is being done is negative. Okay, it's very important that we put this minus sign in there. Now when I go from point B to point C, hopefully you can see that this area right here is just going to be equal to the area that I had when I went from point A to B. So this area of the shaded region right here is the same as the area of the shaded region right here. So what this means is that the work that I do when I go from point B to point C is equal to the work that I did when I went from A to B, and this is equal to 5/2 P0 V0. So the total work that we've done so far is going to be equal to 5 P0 V0, because it's the work that I did when I went from A to B plus the work that I did when I went from B to C. Now when I go from C to D, the volume of the gas doesn't change. So remember that work is equal to pressure times change in volume. So even though the pressure here is changing, because that change in volume is equal to 0, the work that I do when I go from C to D is equal to 0. So we do no work when we go from this point C to D, because the volume of the gas doesn't change. Now when I go from D to E, the volume of the gas is changing, so we have that the work is equal to the area under this graph. Actually, in this case, the pressure is always a constant, so we could literally just say that this is equal to the pressure times the change in the volume. The pressure we have is P0. The change in the volume, I'm going from 3 V0 to V0, so this is 2 V0 change in the volume. So this is equal to 2 P0 V0. And again, we want to look at the sign here. So because the gas is being compressed, right, its volume is decreasing, the work is going to be a positive value. So we have plus P naught, 2 P naught V naught. Finally, when I go from point E to A, we again have a situation where the volume of the gas is not changing. So we have the work that is done when I go from E to A is equal to 0 joules. So the total work that we do during one complete cycle is equal to the work that we do in going from points A to C, and remember this was equal to minus 5 P naught V naught, plus the work that we do in going from C to D, but this is 0, plus the work that we do in going from point D to E. Remember this was plus, I think it was 2 P naught V naught, and then finally the work that we do in going from points E to A, which was 0. So if we add all of this up, we'll see that this is going to be equal to minus 3 P naught V naught. And if we think about this, this is actually equal to the area that is enclosed by this P naught V naught graph. So it's the area of this shape here that's enclosed in this graph. And then we have to be a little bit careful about the sign. So whenever we have a P versus V graph, a cyclic process like this, it's going clockwise. The work that is done on the gas is going to be negative. Okay? So in other words, work is being done by the gas when this process is going around clockwise like this. When the process goes around counterclockwise in the opposite direction, then the work will be positive. So work will be being done on the gas when we have a cyclic process that goes around counterclockwise. So let's go ahead and look at one more example. This example says we have 2.6 moles of a monatomic ideal gas. It expands along a path that's shown on the next slide. The initial temperature of the gas is 158 Kelvin, and it's a three-part problem. The first part asks us to calculate the work that is done by the gas. The second part asks us to calculate the final temperature at point B. And then the third part asks us to calculate the heat that is either gained or lost by the gas when it goes from point A to B. So here's the graph showing the pressure versus volume. So remember, work is just equal to the area underneath this. And so what I'm going to do is I'm going to break this up into two parts. So we've got the area of this rectangle right here. So this is going to be equal to, again, it's base times height. So here the base, so the volume is changing by 8 meters. The height is 2 times 10 to the 5th pascals, plus, and then we're going to have some area that is associated with this triangle up here. So we've got this area up here. So we have plus, and the area of this is a triangle, so it's going to be 1/2 base times height. So the base of this triangle, so we're going from 4 to 8, so the base is going to be 4 meters, or 4 cubic meters, really. I should be careful about the units there. And then the change in the pressure, so this is the height, is 2 times 10 to the 5th. Pascals, of course. So finally, if I plug all this into a calculator, I see that this work is going to be equal to 2 times 10 to the 6th joules. And then lastly, we want to be careful about the sign. So because this gas is expanding, so it starts out at a smaller volume and it expands to a larger volume, the work that is done is going to be negative, right? So the gas is doing work, the gas is expanding, so the work that is done is negative. Now the second part of the question asks us to calculate the temperature at part B. And the way we do this is, if you think about what we're given here, we're actually given the initial pressure and initial volume of the gas, and we're given the final pressure and final volume of the gas. So what we can do is we can use the ideal gas law to calculate the temperature at point B. So the ideal gas law says that PV is equal to nRT. And because the number of moles is not changing, I can rewrite this as PV over T is going to be a constant. So my PA, VA divided by TA is equal to PB, VB over TB. And now if I solve for the temperature at point B, I see that the temperature at point B is equal to the temperature at point A times, so I'm going to multiply this over here and I'm going to move everything else over, so we'll have a PB volume at point B divided by the pressure at point A times the volume at point A. And finally, if I plug these numbers into a calculator, so for example, the pressure at point B is 2 times 10 to the 5th, the pressure at point A is 2 times 10 to the 5th, so these two things cancel out. The pressure at point B is 10 cubic meters, the pressure at point A is 2 cubic meters, so this is just 5 times the temperature at point A. So that's 5 times 158 Kelvin, or 790 Kelvin. So this is how we calculate the temperature at point B. Now the last part asks us to calculate the heat that was either added or lost by the system. And the way we do this is by using the work energy theorem. So the work energy theorem tells us that the change in the internal energy is equal to the heat that is added to the system plus the work that is done on the system. So if I solve for Q, I see that Q is going to be equal to the change in the internal energy minus the work that is done on the system. And because we have a monatomic ideal gas, the change in the internal energy is just 3/2 nR delta T. So we have 3/2. The number of moles that we had was 2.6 moles. The ideal gas constant, remember, is 8.31. The change in temperature, well, the final temperature is 790 Kelvin. The initial temperature was 158 Kelvin. Minus, and we got to be careful about this, remember the work that was done was negative, so it's minus negative 2 times 10 to the 6th joules. So if we plug all these numbers into a calculator, we see that the heat that must have been added to the system is equal to 2.02 times 10 to the 6th joules. So most of the heat went into this work that was being done, and then a little bit into changing the temperature of the gas. Finally, I'd like to talk about the different types of thermodynamic processes. Now, it turns out that in reality, there are an infinite number of ways that you could go from some initial pressure and volume to some final pressure and volume. However, there are certain special types of processes which we can easily describe mathematically and which describe a wide range of phenomenon. So the first one I want to look at is isobaric process. And the prefix iso means to be held constant, and bar is a unit of pressure. So an isobaric process describes a process that occurs at a constant pressure. Now recall that work at a constant pressure is equal to pressure times change in volume. So this is the formula for the work that is done during an isobaric process. An isochoric process is a process that occurs at a constant volume. Now, because work is equal to pressure times change in volume, if the volume doesn't change, the work is going to be equal to 0 joules. So the work that is done during any isochoric process is equal to 0 joules, and this means that the first law of thermodynamics reduces to the change in the internal energy is equal to the heat that is either added or removed from the gas. An isothermal process is a process that occurs at a constant temperature. Now, because the internal energy of a gas is always proportional to the temperature of the gas, if the temperature doesn't change, then the internal energy of the gas doesn't change. So we have that delta U is always going to be equal to 0 joules for an isothermal process, and this means that Q is always going to be equal to minus the work. Finally, there's the adiabatic process, and this is a process that occurs where there is no heat exchange. So this means that Q is equal to 0. And as a result, the first law of thermodynamics reduces to the change in the internal energy is equal to the work that is done on the gas. Now at this point, I want to look a little bit deeper at these isothermal and adiabatic processes, and I'm going to be using a little bit of calculus. So if you haven't taken calculus before, you might just want to skip over this part because it might be a little bit confusing. Now, remember earlier in this video, we said that when the pressure of a gas changes as the gas expands, that the work that is done is equal to the area underneath the pressure versus volume graph. So if I have pressure versus volume, if I have some type of thermodynamic process, say that goes like this, at some initial volume to some final volume, the work that is done is equal to the area that is under this curve. And of course, if you've taken a calculus class, you know that the area under a curve is given by the integral. So if we have an isothermal process, we can actually calculate the work that is done using the ideal gas law. According to the ideal gas law, PV is equal to nRT. So if the temperature is held constant, it means that P is equal to some constant, nRT, divided by the volume. Another way I could write this is I could say it's equal to the initial pressure times the initial volume divided by the volume. So the pressure at any volume is given by the initial pressure and volume divided by the present volume. So we said that the work is going to be equal to the integral going from initial volume to final volume. Actually, I need to be a little bit careful about this. It's actually going to be negative this, right? Because if the gas is expanding, I'm doing negative work. So I have to put this negative sign out front. And it's equal to the integral of pressure dV. So in this case, it's equal to the integral from an initial volume to a final volume of P naught V naught divided by V dV. And because P naught and V naught are a constant, I can pull those out front. So we have P naught V naught minus P naught V naught times the integral from the initial volume to the final volume of dV over V. And this right here, this integral, is equal to the natural log of V. So we'll have the natural log of the final volume minus the natural log of the initial volume, or it's minus P naught V naught times the natural log of the final volume divided by the initial volume. So this is how we calculate the work that is done during an isothermal process. So it's just given by this integral, and we can do this integral for an ideal gas because we know how the pressure and volume will be related when the temperature is held constant for an ideal gas. So now I want to talk just a little bit about an adiabatic process. So an adiabatic process is a little bit more complicated. The basic idea is that we start with the first law of thermodynamics, which says that the change in the internal energy is equal to Q plus W. And for an adiabatic process, Q is equal to 0, so we have the change in the internal energy is equal to the work. And for an ideal monatomic gas, the change in the internal energy is equal to 3/2 nR times the change in temperature. So what I want to do is I want to come up with some type of way to relate the change in the temperature to the work that is being done. So to do this, I want to consider a very small change in temperature and the resulting very small change in the internal energy. So I have that du is equal to 3/2 nR dt, where this dt is a very small change in temperature. And the reason I want to do this is that the work in general requires taking an integral, but the work that is done during a very small change in volume is just equal to P dV. So now what I need to do is I need to find a way to relate dt to P in V. And the way I do this is by using the ideal gas law, which says that PV is equal to nRT. So if I have some change in T, so I have, let's say, an nR delta T, this is equal to the change in PV. So now what I want to do is I want to calculate the change in PV in terms of, P's and dV's and stuff like that. And the way that I do this is I consider what happens if both pressure and volume are a function of time. So what I want to do is I want to calculate the change in PV. And the way I want to do this is by taking the derivative of PV with respect to time and then multiplying this by delta T, right? So the change in PV is approximately equal to the derivative of PV with respect to time times delta T, right? This is the rate that PV changes with respect to time, and then I'm multiplying this by delta T. And this thing becomes exactly equal when this dt over here becomes very small. So if I consider the differential change in PV, this is equal to the derivative of PV with respect to time times dt. And this dt will now cancel with the dt's that appear in the derivatives. So I have that this differential change in PV is equal to the derivative with respect to time of PV times dt. And the derivative of PV with respect to time, we have to use the chain rule, right? If I'm assuming each of these are functions of time, so this is going to be the derivative of P with respect to time times V plus P times the derivative of V with respect to time. And then I multiply this whole thing by dt, which cancels with these dt's down here. So I have that the differential change in PV is equal to V dP plus P dV. And now what I can do is I can plug this expression up here. So I see that the small change in the internal energy is going to be equal to 3/2 times V dP plus P dV. And then finally what I can do is I can use this and relate it to a differential change in work. So we have that the change in the internal energy is equal to the work. So if I have a differential change in the internal energy, this is going to be equal to the differential work that is being done, and that's equal to minus P dV. And this minus sign is here because right when delta V is a positive number and the gas is expanding, the work that is being done is negative. So we have that du is equal to 3/2 P dV plus V dP, and this is equal to minus P dV. So now what I'm going to do is I'm going to subtract this 3/2 P dV to the other side. So I have 3/2 V dP is equal to minus 5/2 P dV. So the 2's cancel. I'm going to divide the 3 over to the other side. So I have V dP is equal to minus 5/3 P dV. And then finally what I want to do is I'm going to divide the pressure over to the other side, and I'm going to divide the volume over to the other side. So I'm going to divide both sides by dP dV. So if I do that, the dP's cancel over here, the dV's cancel over here, and I have V over dV is equal to minus 5/3 P over dP. And the reason I want to do this is I want to have on the left side just pressure and on the right side just volume. And the reason I want to do this is now if I think about this, if I integrate what's on the left, it has to equal to the integral of what's on the right. If these two things are equal, right, if I integrate this, it has to equal to the integral of that. So if I integrate this from some initial some initial volume to some final volume, and I integrate this from some initial pressure to some final pressure, they have to be equal. So if I integrate this, I have the natural log of V final over V initial, and this is equal to, so I can pull out the minus 5/3, and this will be equal to the natural log of P final over P initial. Finally, I can use the algebra rules for natural logarithms, and I can move this in there. So this is the natural log of P final over P initial raised to the minus 5/3 power. Lastly, if I take the exponential of both sides, I have that V final over V initial is equal to P final over P initial raised to the minus 5/3 power, or P initial over P final raised to the 5/3 power. And now what I can do is I want to move all of the final stuff to one side and the initial values to the other side. So if I do that, I have that V final times P final raised to the 5/3 power is equal to V initial times P initial raised to the 5/3 power. Or in other words, V times P raised to the 5/3 power is equal to a constant. And so this gives us the relationship between pressure and volume for an adiabatic process. So if I wanted to calculate the work that is done during an adiabatic process, I could use this to write pressure as a function of volume. So for example, if I did that, I'd have pressure is equal to V naught P naught raised to the 5/3 power divided by V raised to the 3/5 power. So this lets me write pressure as a function of volume. So if I wanted to calculate the work that is done during an adiabatic process, I would just take the integral of this from some initial volume to some final volume. So at this point, I think I'd like to end this video, and in the next video, I'm going to start talking about the second law of thermodynamics.